chapter 11.3, what we're looking at today are nonlinear systems of equations. Now, you might remember us looking at systems of equations before. Maybe x, that's not going to work. So x plus y equals 7, and 2x plus 3y equals 12. And then there were, we could do elimination, we could do substitution. There were other things that we talked about doing to solve a system of equations. These are lines, and so those were linear systems. What we're going to look at today are nonlinear systems. In other words, at least one of those equations is not going to be a line. Now, we've worked earlier in the year with parabolas. That's nonlinear. We just got through graphing circles and ellipses and hyperbolas. So we've graphed a number of nonlinear equations, nonlinear graphs. Now we're looking at systems that involve at least one nonlinear equation that has to be solved. Okay, so we're going to look at two methods. We'll look at one method that's called substitution. You know what that is. We'll talk a little bit more about that in just a minute. And then we'll also use elimination. And again, you know what that is. But as a refresher, we'll run through a couple of examples, and then you'll have some practice problems that you'll get to do on your own. So let's jump in here. So as I just said, a nonlinear, that's not what I was looking for, a nonlinear system of equations means that at least one equation is nonlinear. In other words, at least one equation is not a straight line. And so here we have examples of a straight line. All right, we've got a straight line on each of these graphs. And we have a parabola on each of these graphs. And so just to go ahead and get you to thinking about what and how many solutions you might be looking for, when we see an equation, when we see a system of equations that has a line and a parabola, like these are the things that could happen if we had a line and a parabola. Maybe they don't touch at all, and so this one would have no solutions. Maybe they touch at just one point, and so we would have a single solution. Or maybe that line goes through the parabola and touches it in two different places. So one of the first steps that we need to do when we look at a system, a nonlinear system of equations, is be able to recognize what types of graphs we're looking at and think through how many solutions we might be looking for. Okay, so let's look at our first example. Okay, let's look at our first example here. And spoiler alert, we'll probably use the substitution method to solve this particular nonlinear system. So if we're looking at this first equation, x squared plus y squared equals 20, we've got two options there that this might be. Because of the x and the y both being squared, because the x and y are both positive, we know that we're looking at probably a circle or an ellipse. Now this particular one is a circle because x squared and y squared, they both have the same coefficient. They have a coefficient of 1, and so this would be a circle. But you don't have to know it's a circle. You do have to have a general idea of what this might be. And so this is a circle or an ellipse. If we look at the second equation, okay, both of those variables, x and y, are linear. And so this is going to be a line, right? We would have to be looking at something squared for it to be something other than a line. So what we have here is we have a circle and we've got a line that are going to be on the same graph. So let's think about what our solutions might look like, and then we're going to jump into solving this thing. So it could happen just like I have drawn here, where the circle and the line don't intersect at all. And if this happens, this would be no solution. It could be that this line intersects the circle at just one point, right? We could get just one solution. Or it could be that that line goes somewhere through the circle, and we would have two solutions. Okay, so 0, 1, or 2 solutions is probably what we're looking for, and we could keep playing with this picture, but that's pretty exhaustive of the type of solutions that we would be looking for. So with this one, if we could make coefficients match, like maybe elimination would be the method you would want to use, but there's no way to square down here in this second equation. There's no way to square x or y to make it match something in the top equation that would have to be subtracted. So this is one that, yes, substitution is pretty much going to be the only method of solving other than graphing. We could try to graph this thing and find the intersections, but substitution makes the most sense with this particular equation. So remember what substitution said. I need to have x or y all by itself, and then whatever x or y equal gets plugged into the other equation. So this second equation here looks like it would be really simple to get y by itself here, simply by adding the 2x to the other side. So y equals 2x, and now I know what y equals. Like, I don't know what it equals, but I know it equals 2 times whatever x is. And so now we can take that 2x and go into that first equation, that other equation, and substitute it in for y. And so watch what happens. We have x squared plus, y equals 2x, so the 2x gets plugged in, and that whole thing is going to get squared because all of y gets squared. And this equals 20. Okay? So as we keep kind of working through this, x squared plus 4x squared equals 20. Okay? Now we can add those x squareds together and get 5x squared equals 20. Divide both sides by 5. X squared equals 4. And then this is where I hope I don't lose you, but now that I have to take the square root of both sides, let's not forget that the square root of 4 is both plus and minus 2. Okay? So already I know that my solutions are going to be x equals 2 and y equals something, and x equals negative 2 and y equals something. So those are my solutions. Now, I'm going to choose the easiest equation to go back in and figure out what y can be. And so I'm going to go in that second equation. And actually, with substitution, you get to go right back to that y equals equation. So if positive 2 gets plugged in there, then y equals 4. 2 times 2 is 4. And if negative 2 gets plugged in there, y is negative 4. And so those would be our two solutions. 2, 4, and negative 2, negative 4. Now, I went ahead and graphed this one just so you could see what happens. And so let's go grab that picture. Let's go grab that picture real quick. And there it is. Okay, and so yeah, that first equation was a circle, and the second equation is a line. And let's look at here, 2, 4. Well, 2, 4 is right there, one of my solutions, and negative 2, negative 4 is my other solution. And so that line went right through the origin and hit the circle in 2 spots, and it hit it at exactly those 2 spots. So this is one that graphing would have gotten us to an answer. Notice though that r squared, that would not have been very pretty. And so solving by substitution was definitely the best way to go about doing this one. Okay, so here's our next nonlinear system of equations. And notice what these two equations look like. Again, we've got an x squared and a y squared equaling something. A plus sign in between means, again, that we're looking at a circle or an ellipse. The different numbers in front of x squared and y squared suggest that this is an ellipse. All right, so an ellipse, we're looking at something like this. Okay, x squared minus y squared equals 7. Like, we know what that is, right? This is one of the ones that we just did. Well, so is an ellipse. An ellipse. This is going to be a hyperbola because of the minus sign in between the x squared, y squared. And because the x squared is positive, it's going to open over the x-axis. And so we're looking at something probably like this. And so notice how many times this one can intersect. It could intersect here at 4 different places. Okay, does that make sense? It could, if that parabola, if that hyperbola opens up further out here, we could still be looking at 0. We might be looking at 2, right? If those intersect just at 2 points. So again, we've got a lot of options for how many answers we might be looking for. So we've got to be careful when we're solving this one. Now, we could still use substitution for this one. In other words, we could still get x squared or y squared all by itself and then substitute back into the other equation. But let's just, for the fun of it, let's go ahead and look at what solving this with elimination might look like. And remember what elimination says. I'm going to have 2 variables in separate equations that have opposite coefficients, right? So I can just add those 2 equations together and something gets eliminated. Notice that for this one, the y squareds have different signs already. So if we were to take that second equation there and multiply the whole thing times 2, we would have 2x squared minus 2y squared equals 14. Now we're not going to do anything to this other equation. We're just going to bring it over. 3x squared plus 2y squared equals 66. Now notice what we did here, and we did this on purpose. Plus 2 minus 2. When we add these equations together, those will eliminate. Okay, so 3 plus 2 is 5 x squareds. Plus 2 minus 2, the y squareds were eliminated. And then 66 plus 14 gives us 80. Okay, now we just get to solve. We've only got one variable, so now we just get to solve. Divide both sides by 5, and x squared equals 16. Square root both sides. X equals plus or minus 4. And if you lose that plus or minus 4 right there, then you might lose one of your answers or a set of your answers in this case, because again, we said 0, 2, 4 solutions. That's what we're probably looking for. So let's take x equals positive 4, and the easiest equation to plug it back into seems to be this one. Okay, so let's plug positive 4 into that equation, and let's see what happens. All right, so if we plug x equals 4, we're going to have 4 squared minus y squared equals 7. All right, 4 squared is 16 minus y squared equals 7. subtract 16 from both sides, and negative y squared equals negative 9. Alright, now let's multiply both sides by negative 1, so we have y squared equals a positive 9. And then square rooting both sides, y would equal plus n minus 3. Now, again, here's another one of those places we've got to be careful. What did we substitute in for x? We substituted in x equals 4. And if x equals 4, y equals plus n minus 3. So that's actually two solutions. Okay, x equals 4. Y equals 3. X equals 4. Y equals negative 3. Okay. Now, let's go back and substitute in negative 4. Okay. So, if negative 4 gets substituted in, square it. Now, at this point, like, do you recognize that this equation got to the exact same place that this one did? Okay, if you didn't recognize it, you're just going to keep solving it, and that's fine. Subtract 16 from both sides, and negative y squared equals negative 9. So y squared equals positive 9, and y again equals plus or minus 3. But notice what we plugged in this time. This time we plugged in x equals negative 4. And so when x equals negative 4, y equals 3. And if x equals negative 4, y equals negative 3. And I hear what you're saying, that doesn't even make sense. But doesn't it kind of make sense? Remember that we had an ellipse, which looks something like this, and a hyperbola, which probably looks something like this. And so I think these four answers make sense. Just in case they don't to you, let me drop a picture in here on you. Nope, that's not what I wanted to do. I want to drop a picture on you. And this is the one I'm going to drop on you. And there we go. That's the graph. That is the ellipse. And that is the hyperbola. And notice, 4, 3, 4, negative 3, negative 4, 3, and negative 4, negative 3. Those are the four places where these particular graphs overlap. And so these are our solutions.